Miss Jody here for a second video for chemistry. The first video cut out, and one last point I wasn't able to finish up, and so I'm going to go back and review that point since I had that mishap with that video, and then we'll be moving on today to Le Chatelier's principle that goes along with chemical equilibrium. Okay, so this is chapter 15, or module 15. We have the beginning of the module focusing on the idea of chemical equilibrium. So chemical equilibrium is just the idea that as changes are going on, specifically in the chemical changing world and even the physical change world, there is a balance that can be reached with reactions. And so sometimes the reactions, we look at them as always going one way from reactants to products or whatnot, but we don't really realize that they are actually going both ways. There's what we call the forward reaction and the reverse reaction. And this is a rule of thumb when it comes to chemistry, because the idea is that as the forward reaction is going on, then the products haven't formed yet, but as they begin to form, then eventually there comes a point where the rate of the forward reaction is even to the equal to the rate of the reverse reaction. And so therefore it reaches what we call chemical equilibrium. And so we got the introduction to the equilibrium rule, and then we talked about the equilibrium constant on the next page, and we did some calculations. And then we finished it out with saying, okay, now that we know how to calculate the equilibrium constant, what does that mean and how would you use it? Like, how does this fit to the application of the chemistry world, understanding this chemical equilibrium? And so basically the idea is that it is going to be able to be used as a gauge, kind of giving us an understanding as the reaction takes place. Even though there's that point where it goes back and forth, there's still a point where the reaction will lean and be more weighed toward the product side, or sometimes the reactions are weighed more towards the reactant side. And so we talked about it being used as a gauge, and calculating the K, and if the K is very large, then it's weighed toward the product side. That means you're going to have lots of products that have formed and few reactants. And then vice versa, if your K is a very small number, then you're going to have a lot of reactants and few products that formed. And then there's also that K being close to the number 1, which would give us kind of the balance between the two. And so we talked about these particular signs here. This one being the forward, leaning more towards the forward to the product side, and this one leaning more towards the reverse, back to the reactant side. And then this particular sign being more for the balancing out. Okay, so you remember I kind of wrote that on the side there. You have to squeeze that into your notes since I kind of added that a little later. It's a little bigger there. Then the point that was missed on the first video is once we start looking at calculating the K and figuring out how this all works, we have to note that when it comes to solids and liquids, they are not going to be used in the calculations of finding K. Now, the reason that is, and you got to think of it in this sense, when we are calculating the K, if you remember the equation, there is the bracket world. So you remember the brackets. And anytime you have the brackets, this is an indicator of, in chemistry, for formulas of concentration. So what is concentration? Concentration is basically the solution world, where we have something inside a solution, and how concentrated is it? How many moles per liter? So the main thing to understand is that when the K is wrapped around the idea of the different concentrations, the solid is not really going to be fitting there, right? Because what happens in a solid, you don't have a concentration change at all. You have a mass change, like you can get more of a solid in a chemical reaction as you're making it, or whatever of the reactant, you can lose some of it, but it's not going to change concentration because solids are not in solution, and they're not concentrated. And so it's not a concentration situation. And then liquids, we have the situation of liquids where the density in a liquid is always constant. So what that means is it's different for just a plain old liquid of something versus a concentration of something. Concentration of something is going to be, I'm going to take this one substance and I'm going to mix it with, 4 gallons of water or whatever, 4 liters, because we'd stay in the liters. So I'm taking this much of how many moles of this substance, like this many moles of hydrochloric acid, and I'm going to mix it with a certain amount of water. Okay, that's making a solution. That's creating concentration. But just regular old liquids, like if I was saying, okay, I just have hydrochloric acid just in a liquid, right? Well, that's not a good example, but just something in its liquid form, acetic acid. Okay, then we're not necessarily indicating that it's in concentration. So solids aren't really going to fit with calculating K, nor are liquids. So when you look at a formula and it has the S in parentheses, you're not going to add that to your calculation. When you look and it has the L in parentheses, you're not going to add that to calculation. However, if it does have AQ, if we remember AQ means that it's dissolved in water. It's aqueous. It's an aqueous solution. So therefore, that's a concentration situation. So you have to add that to your particular calculation. So that part was very important. And of course, my video shut off there. All right, now moving on. It's the same sort of thought that we've been on. So this will tie together with the new topic of Le Chatelier's principle. So what this is all about is when a stress, okay, such as a change in concentration, pressure, or temperature is applied to an equilibrium, the reaction will shift in a way that relieves the stress and restores equilibrium. That is actually the principle that this tab is labeled under. So that's the principle of Le Chatelier's principle. And the idea is, when we are talking about equilibrium, we started out with just the idea, okay, the reactants, when it first begins, the reactants have they begin the forward reaction, then eventually the products start forming, and then eventually they both meet somewhere here in the middle, and that's where it gains that chemical equilibrium. So with Le Chatelier's principle, the idea is that equilibrium can be challenged in a sense if you stress the system. So if I'm going to stress the system, that means I'm going to have my original reaction take place. Now this has to be an enclosed system, and the original equilibrium. But then with this principle, the idea is I have my reaction and it's got to the point of chemical equilibrium, and now I'm going to mess with it. I'm going to either add more concentration, or I'm going to add some pressure, or I'm going to add some temperature. So those three things can cause a change in equilibrium. And if you think back to this topic of kinetics, and we talked about how fast we can get reactions going and all that, what can we do to make reactions faster? These were the same sort of things. If you remember, you could increase the temperature, that would help with the reaction more. You could well, with concentration, it was more about surface area. We break it up more, so that really wasn't about concentration. But the idea was taking some principles on messing with the chemical reaction to get it to go faster. This is similar with using these particular three things to mess up the chemical equilibrium. Now, it sounds weird to think, well, why would you want to mess up the chemical equilibrium? Well, the idea is once it reaches that equilibrium and is in the closed system, it's just going to maintain like that. So what if you instead want to produce more product than it normally would? You can mess with the equilibrium to try to get it to keep producing more products. And so there's a reason for messing and stressing the system. Okay, so the idea here in this diagram is this particular formula has H2 in its gas form, and then we have iodine I2 in its gas form, and then we have 2HI in its gas form. So these are all gases, so that's good. We're talking about not using the solids and the liquids when we're trying to calculate some of the things. So not that it matters here in this point, but so here's my little chart here, and these RR is reaction rate, and that would be mole per second. My time is on this side of the graph. Okay, so what will happen? Now at this point, my H, and I, which is the forward reaction, will begin, and then my products will start forming. Eventually, it meets to the point of equilibrium, right? So my pink line is my equilibrium. So once it meets at that point for that, state of equilibrium or whatnot, if I choose to stress the system, I can do something to mess that up, and then I'll have a new chart begin. And so the book gives us the idea of adding H2 into the system. So if I add more H2, then what am I doing? I'm messing with the concentration. So of the three things that I can do to disturb the equilibrium and force the reaction to continue on so that I can get more of whatever I want to get, I have to pick one of those three things, and they all affect different reactions differently. They don't all do the same thing. But in this example, concentration. Okay, so I'm going to increase the concentration. I added more H2. So what will that do? Will the concentration of I2 be greater, lower, or the same as the original equation? So what would you think? So if I add more of this, will my concentration of this be greater, lower, or the same as the original equation in the end? So what would happen? Well, the idea is this. The forward reaction would begin because at first I had all this and I reached equilibrium. Now I've added the more H2, and then this purple line is the second time that the forward reaction takes off and begins to keep reacting. And that's because I've added more concentration, so there's more ability for it to continue with its forward reaction. So it begins with its forward reaction, and during that time, because now I added more H2, then more products are going to be formed. So my products start forming again, and then eventually this second time, it'll reach equilibrium. So with that forward reaction starting, more of this HI is formed. Because obviously if I added more H2, it started the reaction again, so it started using up some of this HI, or some of this I2. Because more products in the end were formed because I added some extra of this. So what does that tell us? Will I still have the same amount of concentration for I, even though I didn't add anything? No, because I added more H2, it started reacting what was there left over of I2 and made more products. So therefore my concentration of I2 is used up because I added more concentration of H2. And so it'll create a whole new process. Now, this situation, when we force an equilibrium to react so that the limiting reactant is always used up, this is what I mean when I say, okay, we want to mess with the system. So I first started my experiment and I got to equilibrium, and then I think to myself, I don't want to get to equilibrium because I still have some of the one of the reactants or what that isn't used up. But do I just leave it that way? No. You add more of the other and change the concentration to force that situation where the equilibrium becomes out of balance again. More H2 is added. It forces the I to be used up. And so this is why scientists would want to mess with the system, mess and stress the system. So by adding concentration, here's an example. They give us CaCO3, this idea of that, and here's your as a solid. Here is your reversible back and forth of equilibrium. CaO as a solid, and then Ca2 as a gas. Now what happens is if you're going through this process and it reaches equilibrium and you say, okay, that's it, and then you say, but I don't want that to be it. I want to keep doing this so I can have more product, then what would you do? Well, if you allow the CO2 during the experiment, instead of having a closed system where, because when you would normally do this in a closed system and it reach equilibrium, nothing can mess with it because it's in a closed system. And we talked about the closed system before. It's when we close up the system, like we put the balloon on top of the baking soda or the container that has the vinegar, and we have the baking soda in the balloon and all that. We seal up the system. Therefore, the products that are formed out of those original reactants are all still there. If you don't put the balloon on, the CO2 just escapes into the air. So therefore, if you measure your products in the end, you won't have the same mass because some of that CO2 will have escaped. So in closed systems, you have to seal up the system. So normally, if I'm sealing up the system here, then I reach equilibrium. But what if I decide to make a way during this reaction for the CO2 to escape? If I keep letting the CO2 escape, then we're not going to have this same equilibrium. Eventually, it's going to have less of this. It's going to stress the system, or stress the equilibrium, and it's going to cause the reaction to continue on because it can't reach that equilibrium. And so this is what scientists will do when they want to create products, more products, out of the reaction that simply would get to a point of equilibrium if it was not stressed. Okay, so the first one, concentration, that's example. Changing the concentration will stress the system, therefore getting you more in your experimenting and stressing the equilibrium. Okay, then the next one, let me move this down here and see. There, I can open this here just a little bit for you so it's not so far away. All right, Chatellier's principle, this is important to note because some of this we were talking about, ignores solids and liquids as a source of stress to equilibrium. So we do have to note solids and liquids, like we were talking about before, they're actually going to be ignored in the idea of stressing the system. So it's not going to help with stressing the system to create that imbalance so that it can't reach equilibrium. All right, so keep that in mind. So the first one was concentration. Now we're going to say pressure and temperature. And we're going to figure out how do they stress the system. Well, pressure is only going to be good to a certain point. Here's the thing. Pressure only affects the concentration of gases. And this makes perfect sense. It's not going to affect the solids. Say I have in my chemical reaction, a block of something that I'm going to react with something else. Adding a bunch of pressure to that block is not going to do anything. It's a solid. When you add pressure, it might crush it, but it's not going to change the concentration. And so it might speed up the reaction if I crush it into smaller pieces. It might speed up the reaction, but it's not going to give me more of a reaction. It's not going to continue on and make the reaction continue past that equilibrium point. So solid's not going to do it. Liquids aren't either, because you know how you can put pressure on a liquid, and that's perfect if you want to make hydraulics and stuff, but it's not going to change the concentration of the liquid. It's not like you can squish water and squish more H2Os together. Whatever you have in that water sample is all the H2O you have. You can push on it, you can try to squeeze it all you want, but you're not going to get more H2Os to do anything different. You're still going to have the same old constant concentration. Well, I shouldn't say concentration, but say the same amount of molecules, okay? But when it comes to a gas, right? And I should also say in aqueous solutions. Now, in the last one, we were talking about chemical equilibrium and calculating the K. We said don't include solids or liquids, but do include AQs because they are solutions dissolved in water. But when it comes to pressure changing the system, no solids, no liquids, and no AQs. Because even if it's an AQ, it's a solution. It's by adding pressure to it, it doesn't change anything. So say I have a certain amount of hydrochloric acid dissolved in water. If I put pressure on it, it doesn't give me more hydrochloric acid. It doesn't give me less water. It just does nothing. It can create pressure to move things, like I said, with hydraulics, but it's not going to help the stress, the reaction to get more out of it. Okay? But the one thing that you can use pressure for is gases. And this makes perfect sense. Remember when we studied gases and we talked about Boyle's law and Charles' law and all that? When you increase the pressure of a gas, you visualize it. You say, okay, here's a bunch of gas molecules. They all want to spread out every which direction. And then I put them in a container and I shove a lid on them and I keep pushing that lid down and keep pushing and pushing and pushing and pushing, whatever one of those presses. Well, what happens is all the gas molecules, they're all still there, which they would normally have spread way far out. But now if you shove them together, that actually does increase something, right? Because you're actually shoving them that would have been way far out, you're shoving them together. So that is going to increase the situation. And so that would be something that pressure would help with. So if I want to stress or mess the reaction, to mess up the chemical equilibrium, if they're all gases, like the original one we did with the hydrogen and the iodine, if I have everything in my gas form, yeah, pressure will work. I can increase the pressure of something, which pretty much makes it like increasing the concentration in a sense. It squeezes them together, and then the reaction will be able to shift, and it will shift in order. Its main goal will be so that it rebalances, gets back to the point of a second equilibrium or whatever, however long you stress the situation out. So pressure will only work with the gases. The last one, temperature. So when it comes to temperature, will that stress or mess the reaction in order to get to mess the equilibrium up so that you can continue the reaction? Yes, because temperature, if you think of it if you remember how we would look at temperature back in the day when we first learned about endothermic and exothermic reactions. Well, first of all, temperature is the amount of energy in the molecules, like how much they're vibrating or whatever, right? And so when we add energy, let's say in a particular chemical reaction like we have here, 2H2O in its gas form, in equilibrium here, 2H2 in its gas form and O2 in its gas form. Okay, now if I look at something like this formula and then it gives me a change in enthalpy, I have this happening at 242 kilojoules. Now, if you remember, because this has been a while, but whenever you end with a positive number here, what you're really saying is that the energy, if it's positive, it did not escape. So therefore, it's got to be put in the formula as energy as a reactant. If the number is negative, then it escaped the reaction and therefore it is exothermic. And so if I rewrote this with my change in enthalpy here, I'd have 2H2O in its gas form plus 242 kilojoules. That's the energy as a reactant. You see it's in there in my reactant form because it's positive, so that means it was back into the system, didn't escape. And then 2H2 in its gas form and O2 in its gas form. So when we're looking at the way we would write it in its formula with understanding basically energy as a reactant or a product, and with this formula, we'd say, okay, so what did this tell me? This told me that during this time, because I've written it now as this is one of my reactants, these two came together, and what will happen? Because this is more energy into the system, then it will force more products to be made. And so then the reaction will shift to the product side, the arrow going that way. And so temperature, if you add temperature to a system, and specifically like this where it's in the system, then it's going to be part of that reactant, making it shift to the product side. And so same, opposite if you remove the energy. So if you remove the energy, so say you have a formula and it came out negative 242. We remember if it came out negative 242, then that would have been written over here on the product side because it would be one of the products. It'd be this plus energy escaping as in this amount of it. And so it would become a product, and then it would give us a opposite direction for what's happening. And so when we look at temperature, we say, okay, temperature can really stress or mess the system too. So we've got concentration, we've got the pressure, and we've got the temperature. Those are the three main things that you can do to stress the system to create more or to mess the equilibrium up so that you can get more of whatever you're trying to make. So they give you an example here in the book, and it says, okay, you have this, the H2 in its gas form, the F2 in its gas form, and you create 2HF in its gas form. And it says, okay, here's the energy of this reaction, the change in the enthalpy, and it's negative 273 kilojoules. And so they say, okay, will it raise the temperature? Or I'm sorry, if we raise the temperature, what will happen? Okay, so we would look at this situation and we'd, let me see which page that one is on. And you can try to do it yourself, answer it, and Chatelier principle, H2. And that is on page, why can't I find it now? Solids and liquids, equilibrium. Oh, there it is. It's on page 546. And so it says that's the following reaction. And here's the change in enthalpy, negative 273 kilojoules. If the reaction has already reached equilibrium, the question will be, what will happen to the concentrations of each substance when the temperature is raised? So when I raise the temperature, See, I tried to not write that out fully, and then I make sure I'm doing it right. So if I raise the temperature, what will happen with this one? After this has already hit equilibrium, what will happen with this guy? What will happen with this guy? So the idea is to try to figure that out looking at the formula and figuring out what we would say would happen in the temperature world. So the answer on that will be on page 546. So try to figure it out yourself and just jimmy it down here. It's not like a real big calculation one. It's just a thought one of trying to figure out what's happening here if you have a change in enthalpy of negative 273 kilojoules, okay? So write that there and then check that. And then the last part of the chapter, I'll do another video on this so that you can separate these two, will be on acid-base equilibrium.